Hi everyone, today we're going to be talking about topic 9.3, Gibbs free energy and thermodynamic favorability. So in our last lecture I was discussing the concept of spontaneity. Or in other words, if a reaction is spontaneous, which means it'll go without any outside energy. Gibbs free energy, or G, is another thermodynamic constant that can describe the energy available in a system that can be used to do work. And you can actually use G to predict spontaneity. So reactions that take place are thermodynamically favorable, which means they are spontaneous. And so you can predict spontaneity by calculating G. Now, technically, delta S of the universe is the best indicator to see if something is favorable or spontaneous. If you remember, for a spontaneous reaction, actually I'll write this down here, but for a spontaneous reaction, the delta S of the universe, which is delta S of the system plus delta S of the surroundings, will always be greater than 0. That's a spontaneous reaction. That's the way you can actually predict favorability, but you typically don't ever really know delta S of the system or surroundings. That's not something you can just easily calculate. And so instead, we can derive a different function that will help us determine that using Gibbs free energy. This is a different state function, but it states that the Gibbs free energy, or G, can be calculated by taking the enthalpy, H, and subtracting it by the temperature of the reaction times the entropy of the reaction. So G is equal to H minus delta S. There's a long way to derive this equation that I'm not going to go through because you don't really need to know, but what you should know is this right here. The free energy, the energy available to do a reaction, is just the enthalpy minus the entropy times the temperature that you do the reaction. Now this is a very important reaction because it relates basically two entire units to each other, and we'll be using it quite a bit. Now, we never really, calculate G, H, or S. We typically always look at the change, right, delta. And so a similar way to say this is that delta G, which is normally what we calculate, equals delta H, the enthalpy, minus T, delta S. And normally we'll have these little knots here. And again, this little symbol just means at standard state, which is 298 Kelvin and 1 atmosphere and 1 mole of what you're reacting. Now let's consider the reaction where A is in equilibrium with B. We can now use Gibbs free energy to predict how the reaction is going to work. If delta G is less than 0, in other words, it's a negative, the forward reaction is spontaneous. Again, that means it occurs without any excess energy. In other words, it is thermodynamically favorable. It will happen without any outside force. If delta G is equal to 0, that means that the reaction is under equilibrium. Right? It's under, or in other words, it's at equilibrium. Right? Rate of the forward reaction is equal to the rate of the reverse reaction. And if delta G is greater than 0 or positive, that means the reverse reaction is spontaneous, or in other words, thermodynamically favorable, and the forward reaction is not thermodynamically favored. So we can use the value of delta G to predict a reaction. Just like with delta H and with delta S, we can calculate standard free energy changes. And so we can use delta GF, where the delta G of the reaction is the sum of delta G's of the products minus the sum of delta G of formation of the reactants. And so over here we see a little table of a state of matter and standard state. For a solid and a liquid, it just means that it's a pure solid or pure liquid. For a gas, it means it's at 1 atmosphere of pressure. That's the meaning of being standard. For a solution, it is 1 molar concentration. And for any element, just like delta H, delta G of formation is 0 because it doesn't take any free energy to form that element. That's how it naturally occurs. Now, of course, because of the function delta G equals delta H minus T delta S, both enthalpy and entropy play a role into whether or not a reaction is thermodynamically favorable. Let's take, for example, what if delta H is less than 0 and delta S is positive, right? In other words, it's an exothermic reaction, and we're getting increasing disorder. In this case, delta G is going to equal a negative number minus whatever T is times a positive number, or delta G is equal to a negative minus a positive value. And so in this case, delta G is going to be negative. And so if I have a reaction that is exothermic and increases disorder, that reaction is always going to be thermodynamically favored. But now let's take a reaction where it's endothermic and I decrease the amount of disorder, or I get more ordered. For example, water freezing. Right, in this case, delta G is going to equal, if delta H is more than greater than 0, it's going to equal a positive number minus T times some sort of a negative number, because delta S is going to be less than 0. Here, delta G is equal to a positive plus a positive, essentially, because I'm multiplying two negative values by each other. And so in this case, delta G is going to be greater than 0, and so it is not spontaneous and not favored. And so a lot of questions are going to ask you to calculate delta G and then tell them whether or not it is spontaneous or favored. Some of them might just have you interpret a process based on what is happening. For example, it'll talk about bonds being broken or formed and, more moles of gas being made, and then you should be able to figure out whether or not it's thermodynamically favored or not based on this equation. Delta G equals delta H minus T delta S. Now here is basically what I just said, but in table form in case you want to have it for your own reference. Right, if we look here, we have delta H, delta S, and minus T delta S, and then we have delta G. And so if delta H is negative, delta S is positive, that means delta G is going to be negative, and it is spontaneous at all temperatures. So for example, ozone turning into oxygen, that is always going to be a spontaneous reaction. The next case is what I also described. It's an endothermic reaction. It's becoming more ordered, and so it's not spontaneous at all temperatures, and that is the reverse of that top reaction. Now we have this case where it's exothermic, but it's becoming more ordered. That means delta G can be positive or negative. It depends on what the value of T is. And so this is spontaneous at low temperatures, but not spontaneous at high temperatures. And the exact case will yield the exact opposite results. And so water going from liquid to a solid at low temperatures, this is spontaneous, right? If it's really cold, it's going to want to freeze. At high temperatures, this isn't going to happen. And the opposite is true for ice melting, right? At high temperatures, ice is always going to melt spontaneously. You don't have to put any extra force into it. But at low temperatures, right, it's not spontaneous. It's not going to want to melt. All right, now let's look at this one practice problem here. We have methane, CH4, plus 2 molecules of oxygen makes CO2 and water, right? This is a combustion reaction. We have the fact that it's an exothermic reaction, and it is becoming more ordered. In other words, we have less microstates. And so the chemical equation above represents the exothermic reaction of methane with oxygen. It says, which of the following best helps explain why the reaction is thermodynamically favored? In other words, delta G is less than 0 at 2,000 Kelvin and 1 atmosphere. So it says the total number of gaseous product molecules is less than the total number of gaseous reactant molecules. Well, if we look, we have on this side 3 gas molecules, and on this side we also have 3 gas molecules. So A can't be the answer. B says the total number of gaseous product molecules is greater than the total number of gaseous reactant molecules. That also isn't true because they're the same. So it has to be either C or D. C says the amount of energy released when the product bonds forms is much less than the amount of energy needed to break the reactant bonds. If this were true, this would mean delta H is greater than 0, but of course it's not. It's less than 0. This is essentially saying it's endothermic. And so therefore D is the only one that makes sense. The amount of energy released when the product bonds form is much greater than the amount of energy needed to break the reactant bonds. And so since we're looking at this from a bonds breaking perspective, we can remember the equation back from Unit 6, where delta H of a reaction equals the bonds broken minus bonds formed. In this case, the bonds formed, this value as a whole is way greater, and so your delta H is going to be less than 0. As a result of that, D can be our only answer. And if you think about it as well, right, delta G equals delta H minus T delta S, right? This must be a spontaneous process because of that equation right there. We'll go over this a little bit more in class so I can clarify anything, but otherwise, that's all. Thanks, guys.